Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, thank you. Thank you for showing up, and that's a huge number. Since it's small and informal, just interrupt me anytime if you have questions or comments and so on. So the first question I usually get is IST what? So I come from IST Austria, which is the Institute of Science and Technology Austria. It's a brand new research institute close to Vienna in Austria, doing basic research, curiosity-driven research, so not trying to develop products, but just follow your own inspiration and do basic research that might or might not be useful one day. So in this respect, it follows the model of Max Planck Society, for example, but it also is modeled after the Weizmann Institute, and it copies stuff from all good research places in the world, so from the US system, from ETH Zurich, and so on. So it's funded by federal law just a few years ago. We're currently growing in all kinds of directions of natural sciences. If you know any physicists, biologists, somebody, computer scientists who want a job in research, send me a mail. Okay, so, and this is it in case you ever want to visit. So my talk will be about image segmentation with topological constraints. And after the advertising that I already did, the main thing I will talk about is a new method that we published at CVPR, or will publish at CVPR 2011, together with Chao Chen, who's a postdoc at IST Austria, working on computational topology, which is why the talk has some aspect of computational topology to it. Okay, so the general problem is foreground, background segmentation. So foreground, you want a binary mask of your foreground in an image to separate it from the background. Very classical problem. So you just phrase it as a prediction function. So you have a certain graph, like a grid, in this case, V. And then you want to predict a labeling that is binary values for each pixel. Is it foreground or background? One is foreground in my notation here. And then you define the foreground region as the set of all pixels that have foreground values. So just very, very easy. So how would you predict such a segmentation? The most popular way is an energy minimization. So you define some kind of energy function, and then you minimize this energy function over all possible labelings. And if you can do that efficiently, you have predicted the labeling that minimizes the energy, and you're happy. And where this function comes from is up to your own choice. So very popular are random field approaches, Markov random field, conditional random fields, and so on. You can also do other stuff like active contours and so on. So I myself will work in the random field setup, where you have a very classical representation. So the energy function that gives a certain energy to a labeling y consists of multiple terms. So first of all, you have some unary terms, that is for each position in your image, so in this grid, for each pixel, which would be a white dot, you have a certain value of predicting foreground and a certain value for predicting background. And then you also have interaction term between neighboring pixels. So between two pixels, you have a certain interaction, which is the pairwise term, and that in our case is just the simplest assumption, since we have only two possible labels. Either the labels are the same or the labels are different. So that is expressed by this pairwise term, where you subtract it. So this just checks are they the same or are they different, the labelings of two pixels. And it's usually a design decision how you want to model this term. So unary terms are usually based on some local image properties, like color value of a pixel and so on. The binary term, you usually want to express that neighboring pixels tend to have the same labeling. So that would be you give a penalization to change label between pixels. And then how strong you penalize, you can also make dependent on the image content. So a popular formula is this contrast-dependent exponential that has proven to be very successful. But everything I talk about is basically, you can construct your terms any way you want. This is just the way people usually do it. So one thing that we introduced, because we need it for the discussion later, is this balancing term. So we have something unary, which tells you for each pixel. You have something pairwise. If you want, you can have higher order terms, but I will ignore them in all the discussion now. And then we have some kind of balancing parameter that weighs the pairwise term versus the unary. So we can discuss the influence, how strong we want this interaction term versus the unary term. So that I will call omega through the talk. And when we have this and the etas have the right properties of defining a submodular function, then you can solve this very efficiently using min-cut, max-flow, so the graph cuts, LP relaxations, or whatever your favorite optimization method is. So this is all very classical. And the effect that you get from these kind of segmentation models is also very classical. So for example, you can do foreground-background segmentation on these kind of images. Typically, you start with some kind of initialization that tells you what should be foreground at all, and then you just refine it. So here you have a trimap given, which has 4 values, despite being a trimap. So white means this is definitely foreground, some human or computer labeled it already. Black means this is definitely background. And then you have 2 intermediate zones, a dark gray, which is definitely background, and you can use it to learn a color model for the background, and the light gray, where you're not sure what it is. So in this case, the task would just be to fill in the lighter gray with either foreground or background pixel to perfectly match the shape. So this is a very typical setup if you want to do user-driven image segmentation in this figure ground setup. So using this background and this foreground, you can learn some kind of color model, and you can get unary terms that tell for each pixel how likely it is to be foreground or background. And this would be the result here. So in the outside, it's definitely background because we already know that. The white one, we know it's foreground. And in between, every pixel, depending on its color, will be more or less likely to be foreground. But this alone is not a good segmentation, obviously. So now you can apply your energy function, minimize it. And if you do that without the pairwise interaction terms, it's just the thresholding. Whenever the likelihood is larger than 1/2, you make it foreground. When it's less than 1/2, you make it background. So this corresponds to this image. And you see there's a lot of tiny noise components and so on, because this field is not necessarily smooth. It might just have a lot of small positive or negative contributions. And when you take this pairwise interactions into account, the image gets smoother and smoother. So with a small contribution from the pairwise terms, a lot of the noise goes away and it becomes smoother. And when you increase the omega even more, you get a nice and smooth outfit of this kind. So that's the smoothing effect that this pairwise term has, and that's the most important role that it plays. The disadvantage of this is that it not only smooths the boundary, it also tries to shorten the boundary. So if you have an object with very thin elongated structures and you increase the smoothing term to get rid of the noise, something like this happens. So with omega really small, you get a lot of noise. In a medium, it's kind of smooth, but you lost some parts of the thin and elongated structure. And when you make it too large, which in the last example looked good, now suddenly you have a completely wrong segmentation because you lost parts. So the smoothing term is good, but it also has negative effects. And the one negative effect that we try to get rid of in this work is that because the smoothing term gets rid of elongated structure, you might break the topology of the segmentation. So if you want to segment this bush somehow, depending on how strong you activate the smoothing term, the connection between the top part and the bottom part will disappear, and you will end up with 2 unconnected segments. Even though you know that no object in the world that looks like this, it can't be unconnected, then it would fall down and something else would happen. So you have prior knowledge in this information. The image, the foreground region must be connected, but it's not expressed in this random field formulation, so you can't really enforce it with the setup that you have. Neither a strong nor a weak smoothing give you the right result. So the topic in this case for the rest of the talk is how can we include such prior information, for example, about the connectedness of the foreground into random field image segmentation. And then hopefully get a result like this, where you have everything is connected and nice in the foreground, but still the noise is removed. So, of course, studying segmentation with topological constraints of this type is not really new. So what you can do is just say, well, I want to minimize my energy, but I also have the knowledge that I want to minimize the energy. But I have the knowledge that I want the foreground to be a connected region. So I just minimize my energy subject to the constraint that the foreground is connected. The problem is this makes it a really hard problem. So even if you don't have the pairwise term, the problem of minimizing the energy subject to the constraint that it's connected is an NP hard problem, where without this constraint, you only have to threshold at 0. Now it's NP hard. So instead of having this hard constraint and saying, well, let's do that as a sign constraint, we can formulate it in a soft way and say, let's define some potential function and say that let's find the minimum of the potential function that is 1 if it is not connected and 0 if it is connected. And turns out this is not really anything else. It's still NP hard to optimize this thing. So if something is NP hard, that doesn't mean that people don't do it, but it's still a bad sign. And the reason why, or one interpretation why this is such a difficult problem with a simple constraint is that topology of a shape, so connectedness, for example, is a really global property. It's really hard to decide on it based on just local evidence. So this is the cover, a setup of the cover from a very popular book by Minsky and Papert, Perceptrons. And the cover exactly shows this, where you have two shapes. One of them is connected, one is not. And if you don't use your finger to trace the lines, it's hardly impossible, at least for me, it's impossible to decide which one is connected, which isn't. You have any guess? Who's in favor of the left?
The left one is connected.
Who is in favor of the right? Nobody's in favor of anything.
We trust Pushmin. We all think the left.
Because you know the cover of the book.
No.
No, it's actually, yes. So the left one is connected, the right one isn't, but I couldn't tell by just from a glance. And in fact, they proved the very popular, famous theorem that tells that no diameter-limited perceptron can decide whether a shape is connected or not. Which means you nearly need something, so the emphasis on diameter-limited. You can't look only at local regions. So just from a view like this, you can't decide if everything is connected or not. You would need something that grows as big as the whole shape, so some global property of the image.
So where was this paper published?
That's the book Perceptrons by Minsky. So there might be a previous paper, but I haven't seen it. It's just a very popular theorem that more or less killed perceptrons for a while. It's the artificial intelligence winter or something started with that. So, like the Ice Age. So it didn't make them very popular in that community. Okay, so of course people have still tried to solve it. It's an interesting problem. So the first work I found is by Zeng et al., where you have some kind of local adjustment of the graph cut algorithm. So you start with the correct segmentation, manually initialized, and then you do some kind of graph cut, but you try not to break the topology while doing it. So this converges to a local optimum, at least according to the paper. I couldn't reproduce it, but I didn't try that hard. Okay, but it still needs manual interaction. You need to first specify the right shape, and then it fixes it a little bit like a level set method, for example. So Sarah Vicente afterwards did a simplified version where instead of saying the foreground has to be completely connected, it's just the constraint, well, you give user-specified pixels, this pixel and that pixel, and you demand that these two must be connected by a path within the foreground. So instead of connecting everything with everything, it's just 2 pixels at a time. And they had an algorithm that is exact if you don't have, pairwise interaction and an approximate solution otherwise. And I guess people here should know about it better because it's work, I guess, done at Microsoft. And there's more work in the same direction. So the bounding box prior is not really connectedness of the foreground, but it has certain aspects of it. So it tells for a user-given bounding box, you want that the foreground segmentation covers the bounding box enough so, that you have no paths from left to right or from top to bottom. So if you have a big gap in the middle, it's not connected, you would have a path. So it kind of finds connected shapes, but it's not the same as demanding connectivity of the foreground.
So actually it's stronger. It's basically saying the object has to be connected.
No.
And
does it?
Yeah. It basically says that the object, it basically says that there has to be a connected component of the object that touches the left path and touches the right path. So the object can have multiple parts, but each part has to be connected in the sense it has to connect from the left part to the right part and from the top to the bottom.
I thought one of the components must.
At least one of the component
must touch enough, yes. So, but you might have a separated component that is not. So we'll see actually an example later of Carlton playing tennis where there is an extra component that the bounding box would not find. Okay. And the last one that is closest to what we do this talk is by Sebastian here in the first row, and me, as it happens. And this is the only one I know which actually targets connectivity of the foreground in this definition that I gave. So the foreground is a region, it has to be connected. So this is the one that I will try to improve on this time. And the work at CVPR is based on a linear program with a lot of constraints, and it doesn't really scale well to huge images. So in this work, I will show an alternative method that solves a slightly different problem, but still in the task of enforcing connectivity of the foreground that is way more efficient and also gives good results. Okay, so first let me define what I'm talking about. So I say the example of connectivity all the time. What we actually try to enforce is to have the foreground should have a specified topology in this following sense. So you have some kind of constraint, TC, of number of components and number of holes. And then you say the foreground object must have at most C connected component and at most H holes. So the case of connectedness means you have only one connected component and you don't care about the number of holes. But everything I talk about can be done also for other constraints. So have two connected components and at most 5 holes. Not sure if it's useful, but it could be enforced in the same way. So connectivity is just the intuitive example that I will give.
If you don't enforce the number of holes, what prevents you from getting this sponge edges and boundaries of the object? Like the penguin, it has a very, for the unaries, it has a very spongy mask after thresholding. So you might end up just with tiny connections that actually connects all these pixels, but still with lots of noise of holes.
Yes. We'll see that later. So this constraint is the mathematical thing of definition. And if you just enforce connectivity and no constraint on holes, you might get something which has like everything is connected, but it has tons of little holes inside. Sure, that can happen. We'll see later in. So the easiest would be to forbid holes, also possible, but not in every case it's useful. Connectivity is a little bit more useful, I think, and. We'll see that later that by using the pairwise smoothing term, we'll get rid of these cases pretty nicely. So just from the constraint, it doesn't follow that you don't have this wiggly boundary. It's true. Okay, so these are the constraints. We call them TC, number of components, number of holes, and that's what we want the foreground to have. And the major step compared to previous work is that instead of solving the classic problem of energy minimization with side constraints, so instead of computing the argmin of an energy subject to this topological constraints, we formulate the problem a slightly different way. And we say, what is the minimal amount of perturbation that we have to apply to the unary potentials, such that afterwards, if we solve with an ordinary energy minimization, the solution is connected. So in formulas, you have your unary's potentials mu. So find other unary potentials you had that are as close as possible to the original unaries, and then after you do segmentation with these unary potentials, you have connectivity. And the intuition behind that is, well, our unaries are estimates anyway. It's not the true likelihood. It's just something we estimate from data anyway. And at the same time, we always have this prior knowledge that the foreground should be connected. So if we do a segmentation with our energy, and we find out, well, it violates our assumption, then we can say, well, then the energy was wrong. So we fix our energy to fulfill the constraints. So, so the question is just, we want to find the unaries that have the right properties, and they should be as close as possible to the real ones. But what does as close as possible mean? Well, they are defined as a vector on every node of the graph, so on every pixel of the image. So we just measure the difference between the two with some LP norm. And we can think of this as a function over the image plane, and then we measure the difference between the two functions. So depending on what kind of norm we use, we get different characterization of what similar is. So if we take an L1 norm, the difference between this unary function and that unary function would be given by the gray area. So the larger the gray area, the more different they are. If we take L infinity norm, then the difference is measured by the biggest difference between the two at any point. So that would be the red bar. But both are valid similarity metrics. So. Yes.
Can you go back one slide? No. Where has the pairwise term gone? I mean,
the pairwise term is still there. So you have your energy function, you leave it as it is, so in our case unary and pairwise. You only change a little bit the unaries here. The pairwise term you leave the same way as it was. You don't influence anything on the pairwise.
So I don't think I understand the constraint on the minimization you are solving with P.
This one. Well, we're not solving over P. P is fixed.
Yeah.
And then we solve for the unaries that make it that cause a connected segmentation. So if you have unaries and make them really, really strong, eventually it will pick these places up and make them foreground.
But there should still be the energy, isn't it?
Why
Actually,
have
the
this
energy,
function?
the
No.
last line is the energy. For y hat is equal to arctan. So that is how.
Yes. So the segmentation that comes from the energy with the modified unaries should be connected.
Basically, you're giving a bias for each.
Yes, so we can influence each pixel to make it more and more likely to become foreground or less and less likely to be. So I have a visualization on the next slide. Maybe that helps a little. Yes.
And why do you target the unaries and not the pairwise potentials? Because connectivity is more into the pairwise rather than the unaries.
Well, the unaries are much easier to influence because, well, they're just values for a certain point. And
I mean, it would have been more sensible to influence the links between pixels. I mean,
not really. The links tell you something if this is the same or not. But by making the links stronger and stronger or weaker and weaker, you can't make something foreground or make something background. With the unaries, you can.
but you make it connected, which is
If you make it very strong.
No, because as it stands, it's just whether it's the same or different, not whether it's both foreground or not.
But
So you could,
Yeah.
if you
Well-
do it on that, you could make it really, really strong that the background is connected as well as the foreground. Yeah.
Okay, yes, you could make it, if you make the pairwise infinitely large, you get everything background, everything foreground, but that's also not what you want, right?
You could change the pairwise, but I don't see
Yes.
a conceptual difference.
Well, you can always argue that you just divide everything and then you get the same if this one gets bigger or that one gets smaller or something, but I think the unaries are just much easier to influence, and for them we have a nice algorithm, and for the other ones we don't. Okay, so...
Sorry, let's go back just 1 second.
Sorry.
So suppose the P norm is the zero norm.
Ooh, okay. Also nice.
So what we're saying is change as few pixels as possible,
Yes.
subject to it being connected.
Yes.
Because obviously what we want to do is search over all connected sets for the energy minimizing configuration.
Yes,
That's
in a
what we
sense,
really
yes.
want to do.
Yes.
So how close do we get if we say change as few pixels as possible to make this connected?
The zero case... The zero case I haven't looked at, and I guess it's going to be hard. So, in fact...
might give us an intuition as to how the one case might behave, or
Yes, it's 2 slides after this one.
Okay.
So I think the zero case and the one case, the one case is related to the Steiner tree problem, because if you have your components, what you really need, if you have multiple, for two components, it's trivial. You just need to find a line.
Shortest path.
And you just need to find a shortest path. For multiple components, it becomes hard because it's directly can be transformed to the Steiner tree problem. And Steiner tree problem, like if you have some nodes, how would you plot a road such that of minimum path length, which connects so that all these cities are connected?
Yeah.
So it's a well-known NP-hard problem, and it's directly related to the L0 and L1.
Yes, I guess the L0, so the L1 means you weigh, somehow you have some kind of terrain and you want to minimize the whole total distance, including the terrain, and L0 would just be the number of pixels, so it would be a flat road. But I'm sure, we didn't look at 0, but I guess it's not going to be easier than the others. No.
L0 and L1, basically for two components, is trivial.
Yep.
As
Trivially impossible.
Yes.
Yes.
Well, with some constraints that we looked at it. Yeah.
So
I guess what I'm
maybe
saying is the intuition at the bottom is not, for me at the moment, that helpful So I'm trying to find another one.
Okay, I'll show you some pictures how it actually works.
Probably will work,
So,
yeah.
I mean, this is not the intuition to change it exactly that way, right? This is just an intuition of not having a constraint, same energy function with an additional constraint, but let's change the energy somehow.
Sure.
And this is the way how we try to change it. It's just the easiest we could come up with. Okay, so this is how you measure the distance. And these are basically all the results we have in the paper, one after the other. So the first thing we look at is if we only have unary terms and no pairwise. And then the result, if we take the difference between the two functions with L1 norm, it's exactly the same as previously minimizing the energy with that as an additional constraint. We'll see that on the next slide. And this means, well, the original was NP hard. This one is also NP hard. We didn't gain anything from this perturbation view. Same way, if you take any p norm between 1 and infinity, we can reduce it to the case of L1. It's not easier than before. So the nice thing that comes up is if we take p equals infinity, so we penalize by the maximum difference we have to do, then it becomes polynomial solvable, in fact quadratic in the number of pixels, and that's not some smart algorithm, that's just the naive algorithm that comes on the next slide. So this is the case that we are interested now, because now we have something where before the formulation was NP hard, now it's really efficiently solvable. We just have to show that it's also useful. And similarly, so this is with unary only. So the case where connectivity is not enforced is just thresholding, really easy. With pairwise terms, it gets more difficult, and we can't show that it's any kind of nice solvability in polynomial time anymore. But we have a heuristic algorithm that just iterates the steps. I will show it in a second. And that solves the problem, maybe not completely optimally, but at least it solves it efficiently and gives connected foreground segmentation with the smoothness term that we want. And I explained this for connectivity, but it's applicable to any of these topological predicates that are defined of number of holes and so on. And we'll see that in a second as well. And the other thing that falls out is that because we only change the unaries and we leave everything else the way it is, the same iterative algorithm will also be applicable to higher order terms. It's basically orthogonal to that. You don't need any, you don't need to change your optimization. You only need to change the unaries and then use the same optimization method you used before. Okay, so just quickly over the two results. So the NP, the result that for p equal 1, it's the same as the classical formulation, follows by just looking at the solutions. So you have the solution without connectivity and with connectivity, and then you compute the difference between the two. So this is not the proof, this is just a sketch of the idea. And you see that, well, we have to adapt the unaries a little bit such that the path that was there before is now also there from the unaries itself. And it turns out that the value you have to change both is exactly the same. So you're minimizing the same function just in different representations. And the case where you have p between 1 and infinity, you can reduce it to the case of L1 by just adapting your unaries with the right square root to make it the same problem as above. So you reduced it from the L1 case. So we have a tech report where this is detailed. So the L infinity case is the most important and interesting one for us. So what does that mean? We're still in the situation where we have only unary potentials, so no pairwise term. So segmentation itself is just given by thresholding. You have certain unaries. If they are less than 0, you make it foreground. If they're bigger than 0, you make it background. So this means it's a sub-level set. Your segmentation is a sub-level set of 0, and you can visualize it in this way. Assume that these are your unary potentials, idealized, of course. Then you have the 0 level, and everything you cut out below the 0 level is your segmentation. So in a sense, you can think if you have this view as a terrain, then each component corresponds to one bassin of this energy function, or unary function in this case. So now if we want to make this connected, we have to somehow take this shape and make it into a connected shape. And for that, we have two possibilities. So we have to eliminate these extra components, and we do that by either merging them to an already existing component, or by discarding the component altogether. That's the only two options we have. I think it's also in Sarah Vichante's paper that these are the operations that might be necessary. So since these components are given by the unary function, what we have to do is we have to perturb the terrain of the unary function such that the components merge or disappear in the right way. So what does it mean to merge two components? Well, if we have this one and that one, if we take the unary function and we lower it a little bit at this position, then we build a bridge here, or canal, and we have combined the two. And similarly, if we want to get rid of this component, we have to raise the unary function a little bit, such that it's above 0 and it disappears as a component.
So I mean, this the level set view only holds when you have when you're considering the unary when marginals, not the unaries, because the unaries are plugged into the pairwise, and the final the solution is obtained after you minimize the energy.
Yes, but we're only looking at the case where there is no pairwise terms. This is just unary only.
Okay.
So it's not useful segmentation, it's just how the method works with only unaries.
Just the reasoning.
Yes.
Actually, I didn't fully understand this basins. What is actually exactly the visualization there?
So this is the three-dimensional view of the unary function. I mean, it's not the real unaries, it's just the function that in the case of an energy would be the unaries. So here the unaries are large, here the unaries are small.
And negative.
And negative, because this is the zero set.
Yeah.
So it's not as real unaries look like, of course. It's the visualization of a function and level set below it. Okay? So then the options are just, you have to change this function to make the right components, either by lowering it or by raising it. And you can compute the cost of that. So if you want to raise an entire bassin above the ground level, so this case, to get rid of this component, the cost in alpha infinity is the maximal depth of that bassin, because that's the maximum amount you have to change, plus the tiny epsilon to make it above. But the epsilon is arbitrarily small, so we can just ignore it. So the L1 cost would be the sum over all unaries, but in the L infinity case, it's just the maximal value. And the same if you want to build, if you connect two components, you have to dig a certain canal into the function. So instead of being larger than 0, it has to be a little canal to make it connected. And the cost of that is the maximal height anywhere along this path where you build the canal. So then, if you want to decide, should I connect a component or should I discard the component, you want to minimize your costs. So it's either that cost or that cost. So the one you choose is the one with smaller value. And then you have made this into that function, basically. So,
But isn't there an explosion about like combinatorial?
yes. Yes. So far, this is nice and intuitive, but it's not efficient. So if you have a real image, you have a lot of, this is unary only, remember? So if you do just the thresholding, you have a lot of tiny components that are, and getting rid of the component is easy. You just see the maximum value in this component. But connecting it to everything else means you have to look at all possible paths to all other components to make it connected. And that's not a very efficient thing. You would have a lot of components a lot of paths to look at.
Even not triple, there could be like a path which serves 3 at the same time, and that might be more efficient than doing individual
Yes.
ones.
And if you take L1, this is exactly what happens. The same discussion holds for L1. And then connecting something will influence something else that might be connected and so on. And it gets a big mess. So the L infinity case is nice because you have theorems from computational topology. And with this L infinity, it's actually the case that one connection does not influence another. Because the worst case is what determines your connection, and everything else is not affected by the worst case along that line. It doesn't change what else you have to change. And in particular, there's a theorem by Paul Bendich that you don't have to look at all possible paths between all possible components for connection, but for each component there's a critical point, so that's a point of zero derivative in your space of unary function, or in the unary function. There's a critical point that determines how costly it is to eliminate this component, where eliminating means connecting with the path. So it's easy to look up how to get rid of it completely. It's just the value of the maximum within. And you also need to find one point in the image that determines exactly the value of building a canal to it. So that's the difference to the L1 situation where you can do that. So the algorithm works in a sense like that. Not only can we can show there is some kind of point that has this property, but we can also compute all of these critical points for the whole image efficiently by a merging tree construction. So basically, you start with a low value and like a level set. You raise your value, and neighboring pixels that have this value in the set are merged, and you get a tree where all pixels somehow merge until you get the maximal value of all possibilities. It's very similar to level set method segmentation. So what you end up with is a tree like this, and at a certain level your points are above 0 and others are below 0. And each subtree below 0 is one component of your original segmentation. Yes?
Would the complexity change if you only have a smaller, if the unary energies are not unique, but you have a smaller discretized set, say from a unary decision tree or something, you only have 1,000 different values instead of 1 million for a megapixel image?
I don't think so. I'm not saying this is the best you can do. It's just the naive implementation of building this merging tree, and you need to compare to your neighbors. Maybe it's a terrible estimate. But the values themselves don't make a big difference because you have to iterate over all pixels and build this tree.
Mm-hmm. But to connect to neighbors, you still have to do some shortest path or not?
No. So the nice thing is, from this tree, you can immediately read off the cost of discarding everything. So this is one component, this is one component. Filling up the gap to get rid of the component means you have to make all of these points larger than 0, and the cost of that is given by the minimal value. No problem there. The nice thing is that in this tree, you can also merge these components by having this path and pushing the whole path below 0. And this is exactly the cost of the maximal value along this path. And this path is in the tree, so you don't need to compare all possible paths. But this merging construction gives you the one path. It's not unique, but this path will make it connected. And the value of this point is optimal.
And to find this path, you just...
To find this path is just every pixel is connected to every other pixel in this tree somehow. So you just have to find in the tree the connecting path. You go up, 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 up until you meet. Okay. Okay. It's a nice construction, and we can maybe discuss it afterwards if you need some examples. Okay, so that's the case of unary only. We can just, for each component, we compute these two values. We know which one to use, and the smaller one we use to connect them or to completely discard them. So when we have not only unary potentials but also pairwise potentials, the situation is a bit more difficult, because now the segmentation does not correspond to the sub-level set of the unaries anymore. So we don't have an optimal algorithm, and maybe there doesn't exist one of this simple kind. But what we can do is we can take an existing segmentation, for example, from the ordinary pairwise graph cut, and then we can construct a new function from this where the sub-level set property is fulfilled. So basically, we have some kind of unary function. This is the region of segmentation foreground. This is background. This is background. Then we construct a function from that where just the foreground is pushed down and the background is pushed up. Then we have this property of sub-level set, everything below 0, everything above 0 again. And then we can apply the same algorithm as before, build our merging tree. And we know that this property of if we shift the top half the same amount as we shift the bottom half, then this comparison, what is more costly, this one or that one, is still fulfilled. So this gives us an algorithm where even with a pairwise term, we enforce we can compute the cost for this function, and this function we can plug into our energy again. So the nice thing is, if you actually didn't have pairwise terms, this construction doesn't change anything. So if omega is 0, you get the same results as before. Okay, so this is the whole algorithm, and it's exactly what I told you in words. So you start, you do some kind of segmentation of your image using no topological constraints, just energy minimization. If this does not fulfill your properties, you create this auxiliary function, shifting stuff up and down. You compute the modified version of that. You adapt your unaries by the modification, and then you resolve. And you know that what originally was maybe unconnected, if it was unary only, it would be forced to be connected now. Since you have pairwise terms, there might still something go wrong. So if you still don't fulfill your properties, you have to correct again until it works. But again, if you don't have unaries, this is pairwise, this is exactly the same as before. And otherwise, this will need a few iterations. So there's no guarantee that you get the optimal solution, but it gives you a connected solution after very few iterations. So.
Finitely convergent?
Is it finitely convergent? What does it mean?
Can it cycle?
No. Your energy, you always adapt the... So you compute what the maximal perturbation is that you need, and in the next iteration, the perturbation will be less or equal. So the pairwise might break things, but it cannot go back to the original setup or something. Yes.
So Christoph, here the point was here, right? If you had used min-marginals instead of just unipotent, you would just need one iteration.
But I can't influence the marginals directly, right?
Why not? The margin. So exactly, the marginals are directly the effect on the marginals. If you change the unary, that is a lower bound on the effect on the min-marginal. So if you change the unary cost by 5 units, then the min-marginal will at least be affected by 5 units.
Okay. Yeah, maybe that's the way to make it nice for the pairwise situation. You're right. Yeah, we should discuss that. Thanks. Okay. Enough formulas. Let's look at what happens. So we have our tree. The first segmentation is not connected. This is the function of the unaries. By this construction shifting up and down, the offset changes a little, so we see the outline of the original segmentation here. We adapt this function to be connected with a path that we found from this tree construction. So this is the path here. It's just a 1 pixel line, a bit wiggly, because we don't shorten or do anything. We just say, give me a path where the value is minimal along every point. This gives me adjusted function. The adjusted function gives us adjusted marginals. And if we then resolve with a graph cut, we get a connected segmentation. It's not guaranteed, but in this case, it worked. After one iteration, it was already done. Okay, so here's some example. This is the tree with different strength of the pairwise. And every time we enforce connectivity, here we have Carsten doing something. And you see that the usual graph cut will disconnect the foot and the leg. But if the evidence of the foot is strong enough that the algorithm decides not to discard the foot, but keep it, so we save Carsten from losing his foot. And depending on the strength of the pairwise, it looks good, or at least it's connected. Okay, this young lady, same thing. The feet keep connected. And this is the example where the bounding box, for example, would not work. I mean, because you would, if you see this one, or this one here, if you collect one of them, the bounding box will be fulfilled, but the second one might not be connected. I mean, it's the only case that maybe it makes a difference. But sorry for using your picture again. It's just, it works so well for you. I don't know why. Yeah, that's sorry for that. So that shows the other thing, that we start with this graph cut segmentation and we adapt it to make it the right properties. Here the graph cut lost the foot. There is no way we would restore it, because there's no reason to invent a new component. We only fix what is there. And the same would hold for the L1 energy minimization. There's no reason to hallucinate a lag here. So. Okay, so we also did numerical experiments. You can see them in the manuscript. Basically, the result is that using this for this grab cut data, where you actually know everything is connected, it gives a little bit of improvement, but not much. And not much for two reasons. One reason is that stuff that is connected to connection pixels are really not many. So semantically it makes a difference, but just from the pixels it's not a big difference. And the other thing is that whenever your original segmentation is connected, nothing changes at all, because it's already happy. And for many of the images, the original segmentation, if it's just a lemon, it's connected anyway, so nothing changes anyway. Okay, so the one thing that is kind of puzzling is, well, we have this little path that connects in the unaries our one part and another part. So why in the end then we get a nice leg out of that? And that's really only the effect of the pairwise terms, which is with this contrast sensitivity. So we enforce some unaries, so we enforce basically that these will be foreground pixels, like a user stroke. And then, because the pairwise terms say, well, move the foreground region such that it ends as a real image boundary. So then, instead of just keeping these, it will move everything to the real boundary, which happened to be the lag. Yes?
So, I mean, my experience, we played quite a lot with that, but I mean, so actually, if there are only two components, I mean, you might get the global optimum with some other method, right?
Maybe, I don't know.
Yeah, I mean, I don't know, like shortest path and the min-marginals and the
Okay.
various things. But my experience, actually, most of the time the results doesn't look good because the unaries are not supporting it. I mean, the pairwise terms can, in some cases, as here, can snap to it, but it's very often not the case. Typically, what you want to add is has some different color, and the best solution, the minimum cost solution, is just like cutting out a 1 pixel path of this leg because the unaries do not support it at all. All the other pixels, you pay all the other unary costs for the whole leg, and that's just normally much more than this extra what you gain with the contrast. So maybe you could check if it's actually the optimal solution.
Right. Maybe we are actually lucky in this situation because the path we get is not straight. If it's straight, it's like the shortest number of unary or pairwise to violate. Because we have some kind of wiggle because we enforce shortness. Maybe that's what kicks it over. Because then actually left and right is shorter than the wiggle.
So just one comment, like when Sarah did the Dijkstra GCC, most of the time finds also path shapes. Compare it to what Victor has done on the bounding box, where the solutions are most of the time nicer. Actually, she gets lower energies and they look horrible because they're like thin connections and they just don't look nice. And it's probably the energy function is actually pretty wrong.
Yep. Either our color model is good, which I doubt, it's the simplest we had built in, or it's really that the wiggles of the path make it more likely to make it a bigger region, because otherwise you have too many pairwise cut.
Can we see the unaries again for this one?
You do, but I guess you can't see them well. Let's see. No.
We kind of see them once we see 5.
So the zoom in is on
right. No, that's the phi, so it's already pushed up and down.
But that shows us which side of 0 they were on?
Yes. No, it shows which side of what the segmentation, the original segmentation said. So it pushed these ones below 0, even though they might have been above 0 a little bit. Maybe in the paper we have the unaries. I don't remember exactly.
So push them below 0, which means
but just for that means, above 0. So because they're not part of the graph cut segmentation, they look darker than they need to be in this case.
Yeah, so it's been made harder.
No, because this is just for computing the path. Afterwards, we use the original unaries, and only this path is what's added. This is just the hack to compute something below 0, above 0 district. We might use the unaries instead. We observed that it works pretty well. Maybe it's a combination of this long wiggle path and a color model.
So your adjustment of the unaries, would they always prefer to connect things, or would they decide, for example, that this is the tiny sock down there? Is too small, and
it can discard things, but it's not based on size. It's based on depth, in a sense. So the maximal value will decide, which is kind of counterintuitive when you think about the energy. But so a large component that is barely above 0 might completely be discarded. Below 0 might be discarded because the minimal value is pretty weak.
So, Christoph,
yes.
I tried something which is very similar 2 years ago,
okay.
Which was in the unary potentials. You can compute so if you just look at the unary potential, I was looking at it with marginals, and then computing shortest path using Dijkstra. And in the Dijkstra algorithm, what you can do, instead of computing the L1, because Dijkstra is basically summing the things up. What you can do is just raise the weights to a power,
okay,
and basically that is exactly you will be there computing the
LP case, yes, yes.
Yeah, so with Christoph Riemann, I think we had this.
Where?
When did we publish CVIU 2010, right? Yeah. So basically, it's not directly. It's related.
No, it's the LP case then, right?
Yes, it's basically we looked at different P. What should be the P and.
Okay.
Yeah, we looked at different P norms.
I keep missing CVPR papers, it seems.
It's pretty hidden somewhere.
Yes, it was the main thing about that paper was the matting stuff.
Oh.
Okay. Because we're using.
We have a nice spider where there are legs and some components you take out, some in. We do just control all the possible ones. We have connect, not connect, take in or out according to the energy.
Well, I mean, the nice thing here is really that you get the exact solution for the L infinity case. For the LP, it's still a mess. So. Okay, and the L infinity works only because you have arbitrarily many components, but they don't influence each other in the sense. So for all the LPs, they influence each other, and maybe it looks better. I don't know. Okay, so the other thing we did, and here's the visualization that we might not need anymore. So you have the unary terms, and this would be the graph cut segmentation. Then if you fix this using the L1, you get something like this, and forget that one, that's a mistake. So it just looks for the shortest amount of unaries to add up, which is this one. But if you have a certain path of of relatively close to foreground, it will use that one instead. So I guess that's the same example. It's a really high P. Yep. Okay, even better. So the other thing is we try to understand why is L infinity useful at all, or is it just weird version of L1? So we did some synthetic experiment to compare this L infinity case to the previous L1 case from Sebastian. So we needed small images because they didn't scale to large images. And we looked at the case of uncorrelated noise, so you can have individual pixels with a large value. Or we looked at correlated noise, which to me is more realistic for natural images. If your color model is wrong, you might get components somewhere. It's not just random noise on top. And just to sum this up, not to go over time too much. So if you have uncorrelated or really weakly correlated noise, then how to read these things? You have noise strength in the y-axis and strength of the pairwise term in the x-axis. And, well, less noise is better. And then if you have certain noise, there's a certain maximum how strong you should use your pairwise terms. And this is the difference in error between the L infinity connected version and the graph cut, a heuristic of just keeping the largest component of the graph cut and the connected MRF from Sebastian. And you see in the uncorrelated case, there's larger regions. So if you have strong noise but weak pairwise terms, that means your original segmentation will have many small dots which are unconnected, but they might have a strong value in the unary. And then we will try to connect them because we only care about the strength of the unary, not about the length of the path. So then L infinity is not a good measurement. The nice thing was that once we went to more correlated noise, like whole blobs, turns out that then we get better than the component heuristic or something. Okay, so another thing here is we have this X shape, and if you have individual pixels in between that are noisy, it will not make it unconnected. Usually it will make it change the shape, but it will not make it completely unconnected. So the heuristic of just keeping the largest component, ignoring everything else works quite well. And when you have correlated larger noise, you might really disconnect parts, and then it really helps to connect them again. So with the weak noise, it's kind of not better than anything else, maybe worse. But once you have correlated noise, it turns out that it's more or less, everything here is green, so it's basically the same as the connected MRF. And you have several regions where it's actually better than just using the graph cut itself. So fixing the topology actually helps you in terms of mistakes in the number of pixels. Okay, and that's, I guess, it. So the idea that I wanted to present is that you don't look at energy minimization with additional constraints as a constraint optimization problem, but as sometimes you view it as your energy function was wrong, how to fix it, and we can fix it by unary function potential because that's the easiest we could do. And in this connectivity example, it's actually, you can solve it now efficiently what you couldn't solve before. So that's our main, we were most happy about that. You actually break the NP hardness by switching to a different norm. And the nice thing is because you only influence the unaries, you never change your optimization method. That works for any unaries anyway. So everything that was submodular stays submodular and so on. You can just plug arbitrary other higher order terms into it. Yeah, we have code. And okay, so the one point that might be arguable is connectivity useful at all? Because usually you don't know that you have a bush in the image and you want to connect the parts. So, and I think for natural images, connectivity is not a really strong prior to use for anything. But there's medical application in 3D when you have like vein systems or other medical parts, where you really know that it's connected and it doesn't have loops and so on. So to make it work in 3D and efficient there is the next obvious stage where it's actually useful, something practical than just proving theorem. Okay, thanks.